So for the rest of our time today, and probably next class as well, let's talk about optimal decision thresholds. So up till now, I've given you the threshold value Z, and now I'm going to show you how to calculate the optimal threshold for yourself. So this will proceed. The next major topic we cover will be the optimal filter. So once I cover both optimal thresholds and optimal filters, then if I give you the modulation functions, you'll be able to basically design the rest of the system yourself. So given modulation signals S0K, S1K, and HK, and the detection filter HK, what is the optimal Z? So intuitively, we sort of had this. So this is the PDF given that a 0 was sent, and this is the PDF given that a 1 was sent. And usually, so far we've had S1 equals minus S0. And under those circumstances, I've generally said the threshold should be set to 0. So intuitively, because the noise is indistinguishable on both sides, intuitively what I've generally done is I've gone right in the middle. I've taken the halfway point between these two means and picked that as my threshold. So on this side I decide 0, and on this side I decide 1. Because of the symmetry of the Gaussians, what you'll see is that that's the point where the two Gaussians cross over. So in other words, here is where 1 is more likely, and here is where 0 is more likely. So you can interpret, if I receive this value, let's say 0.5, then the probability that a 1 was sent and resulted in 0.5 is this. And the probability that a 0 was sent and resulted in 0.5 is that. So on either side of the decision threshold, we're picking the most likely value for the bit. So this is what's called maximum likelihood detection. But we can show in some detail that that's actually correct. And in fact, we can go further. So another issue is this. Remember that my probability of error expression, just from the last example, my probability of error expression was this: 1/2 root C root TS S0 over N0. And when I plugged in all the values, I got this. I got 2.34 times 10 to the minus 3. So remember, leading up to this point, what happened was it didn't matter what the probability of 0 and the probability of 1 were, because they both came out of the expression. That happens to be a quirk of the particular threshold that I picked. That particular threshold is optimal if, and only if, the two bits are equally probable. But let's think about this. This probability of error expression doesn't involve the bit probabilities. So what I could say is, suppose probability of 1 is equal to, probability of 1 is equal to 0.999, and the probability of 0 is equal to 0.001. So I could use a threshold Z equals 0 could always pick 1. I could forget about detection, throw out my receiver, and just always pick 1, and my probability of error would be 0.001, which is less than 2.34 minus 3. So clearly, a threshold of 0, a threshold that's halfway in between the two means, is not always optimal. In this case, it's better, although still not optimal, to pick a threshold that is basically infinity. In other words, anything less than infinity, I map to a 1. So my question is, if one bit is significantly more likely than the other, how does that impact the decision threshold? Okay, so to do this, what we're going to do is we're just going to brute force it from calculus and basically find the maximum in the way that you basically did in your first year calculus course, or the minimum, excuse me. So what is probability of error? The general form is this. One half root c S0 minus z divided by 2 root 2 sigma squared times probability of 0 plus 1/2 root c of z minus s1 divided by root 2 sigma squared. Probability that the bit is a 1. Okay. What do I do now? What I need to do is I need to take the first derivative of probability of error with respect to z. So d by dz, the probability of error, is equal to, I'm going to take out everything that's a constant with respect to z. That's 1/2 and probability 0. D by dz, or c, that's 0 minus z divided by root 2 sigma squared, plus 1/2 probability 1, d by dz, or c, z minus s1 over root 2 sigma squared. Okay, what is d by dz over c? Well, we can use the chain rule of derivatives, which means that all we really need to know is what is d by dx over c of x. So remember that. Let's remember the definition of erf c. Erf cx is the integral from x to infinity of...
So, is there 1 over root pi?
1 over root pi?
For cx?
Yes. I just didn't take it out of the integral, but yeah. It's actually 2 over root pi. 2 over root pi of e to the minus t. I'll use t as a dummy variable integration. E to the minus t squared dt